Hi, I'm Sasha. I am a student at Scripps Institution of Oceanography studying marine biodiversity and conservation. Before Scripps, I worked as a security engineer in the tech industry for almost 10 years. I came to Scripps because I wanted to see how I could apply my technology background to ocean conservation. One area of ocean tech that always interested me was autonomous underwater vehicles. They were like robotic submarines, and I was fascinated with how they worked and how they could be used to inform conservation efforts. To learn more, my friends and I interviewed Jen Walsh, a research biologist at NOAA's Antarctic Ecosystem Research Division, and an expert AUV glider pilot.
So this is an autonomous underwater glider, and we use these to conduct ecosystem surveys both in the Southern Ocean and off of the California coast. So these gliders can collect a whole suite of data depending on the sensors that they have installed on them. So for example, our typical glider in Antarctica will have a conductivity temperature depth sensor, or a CTD, and that will give us measurements of temperature and salinity. We also have an oxygen sensor on them, which will give us an idea about primary productivity. They have an optical sensor on them that will measure chlorophyll, colored dissolved organic matter, and backscatter. Again, that gives us a sense of what the prey field might look like for zooplankton that feed on algae. And our most important sensor that we have on them is an echo sounder for active acoustics, and that allows us to obtain a biomass estimate of Antarctic krill. Not every glider has it, but occasionally we'll have a camera on the glider, and we have two different types of cameras. We have one that's integrated into this black section here, which is called our science bay, and that camera's role is to take pictures of whatever zooplankton is in the water that the glider happens to be going through at that moment in order to validate acoustic targets. And then we have another type of camera that we mount on these gliders, and this is an example of that, and this is called a shadowgraph camera. And this mounts on the nose of the glider, like so. Actually, it's upside down, like so. And this has a light source on one side and an image detector on the other side, and as water flows through this, it will take pictures of the shadows of very, very tiny organisms as the glider flies through them. So that allows us to collect some data about the density and abundance and distribution of really small zooplankton communities that our acoustics won't pick up. We collect gigabytes of data with these gliders, and a typical deployment could be almost 1 million images from a camera. So we are currently developing pipelines for data analysis. As you can imagine, these data sets are much bigger than anything we've ever collected in the past. So we're working with the Google Cloud platform and virtual machines in order to be able to analyze these data, because the data sets are just too big to live on local machines or even servers. So we're working in the Google Cloud, and we're working with AI machine learning software to be able to analyze images rapidly, which involves having to build out models using reference sets of images. So these are all things we're still working on. We're relatively new to the glider world. We've been doing this for about 6 years, and it was a rapid switch for us. So all of that is in the works.
Jen talking about all the data that can be processed using AI got me thinking. How can we use the data gathered from the AUVs to inform policy decisions? We knew that the AUV data would need to be combined with data from other sources to most effectively conduct marine spatial planning. I pictured a fishbowl that already contained the ocean. Now insert terabytes of potential data. It's enough to make your head explode. How does it all come together to form something useful? My friends and I drove up to UC Santa Barbara to meet with Dr. Will McClintock, a senior fellow at the National Center for Ecological Analysis and Synthesis. Will and his team created SeaSketch, a tool we had learned about in class.
SeaSketch is a software service, a web-based application that's used for collaborative geodesign, which is really just a collaborative drawing of zones that could be marine protected areas, aquaculture zones, shipping lanes. The data that goes into SeaSketch comes from a variety of different sources. Government is typical, so agencies like NOAA, National Park Service, or USGS, they have data on bathymetry, right, for example. Academic institutions, researchers collecting information on species distribution, for example. NGOs, like the Nature Conservancy or Wildlife Conservation Society or WWF, all these groups are doing research and gathering data for different purposes, and so they're invited to the table. Last week I was in Kiribati. We got hired to go there and stand up a system in a day, right? So we just, 20 people showed up with their data, we got it all into the system. You know, by the end of the week they had a complete system, which is one of the biggest problems with making progress in marine conservation, is just making sure you have a system to hold all the data that then can be used for decision making.
I loved learning about how C-Sketch made it easier to design MPAs and centralize disparate data sources into one resource for marine spatial planning. But now that we had all the data centralized, I wondered how we could make sure these tools were accessible not just to us as technologists, but to the general public and policymakers as well. My core question was still whether there was a way to use technology to make conservation efforts more efficient and effective. Jen and Will both had some answers for that one too.
These gliders, they're an initial investment for sure, but once you have them and you maintain them and you don't lose them, you can redeploy them over and over again. You still need a couple of ship days, one to deploy, one to recover. But after that, they're incredibly cost effective to collect really a lot of comparable data that we were able to get from a ship.
The problem was that the technology we used back then was not exactly the kind of technology that your average stakeholder could wrap their heads around. And what's crazy about that whole thing is not just the extra work that it adds, but it's disempowering, because people generally, in my experience, like to learn new technology, especially if it's a fancy, flashy thing they've never seen before. Like being able to have the opportunity to sit down, learn how to use this thing, and then contribute, information and ideas through that technology. That's pretty exciting. It doesn't feel like you're speeding it up. In a way, it feels like you're slowing things down. And you're slowing down the conversation and then using this tool as a conversation piece.
Technology can't work in a vacuum. If we want to maximize our potential to achieve 30 by 30, it's going to require all of us working together, engaging stakeholders, collaborating, and learning from each other. We can't wait for what the future holds. Are you in?
Do you want me, is that the right setting? Do you know what the right setting is?
Well, Lev said he's pacing around his apartment. We can just call Lev. Lev, dude,
What do we do?
give me an answer, Lev.
It's like when you stop talking, it goes over. I don't know